Good morning, everybody, or good evening, rather, everyone. This is Chris with the Ancient Scholar. So today we're going to be continuing pathophysiology, and we're going to transition into talking about acid-base balance. Now, I believe about a week ago, actually it was just a few hours ago for me, but a week ago for you guys, you should have completed a series of 4 videos on pH. And the assignment that you had to do at the end of that week will relate directly to the concepts that we'll be talking about in the next few videos, and that is acid-base balance. So you should at this point understand what pH is, what it measures, how we measure it, what a logarithm is, and then what we're going to do is we're going to add on to those concepts that we talked about earlier, and start talking about some of the pathophysiological concepts involved. So we know what an acid is, and we'll stick with a Bronsted-Lowry definition of an acid is any substance that can donate hydrogen ions. And a hydrogen ion, of course, is positively charged hydrogen. It's a hydrogen without an electron. It's basically, well, it's not basically, it is a proton floating around. Generally, that proton will be attracted to the oxygen part of a water molecule because the oxygen it takes on a partial negative charge because water is a polar molecule. And we call that a hydronium ion. Generally speaking, hydrogen ion, there we go again with the clock, a hydrogen ion, a proton, a hydronium ion, we consider analogous statements. We say it's all the same thing. Okay, so before we get into talking about some of the conditions in acid-base balance, let's just talk about the body. The body likes to maintain a certain pH, pH that's normal for the body. We know if we get too acidic or too alkalotic, certain processes can shut down. Proteins are especially sensitive to pH changes, and you guys should have covered this in chemistry if you remember talking about amino acids and proteins and Zwitter ions, and kind of how acids can change the specialized structures of proteins and change the protein conformation and make a protein act differently than it would normally or not act at all in some cases. So pH balance is very important to ensure that biological processes within our body can occur normally. Generally, when our pH becomes out of range, that means something's wrong with our body. A lot of people, and it's somewhat maybe a pet peeve of mine, I suppose, people will say, oh, his pH is low, he's really acidotic, we need to intubate him or whatever it is because of his pH. Well, that may very well be, but we always need to recognize this fact, that the pH just doesn't arbitrarily change. Okay, acidosis, which is a state of elevated acids in the body, and alkalosis is a state of low acids or elevated base in the body. Acidosis is not really a formal diagnosis. You're not going to see somebody diagnosed with acidosis. If a patient is experiencing acidosis or experiencing alkalosis, an acid-base balance problem, that problem is caused by something. So we always need to recognize that when we assess their pH and we look at the arterial blood gas, which you guys will be talking about toward the end of the semester in lab and lecture, and actually doing arterial blood gases, drawing them and interpreting them next semester in the clinical environment, when we talk about somebody having altered acid-base balance, we are talking about a problem. The acid just doesn't arbitrarily change on its own. If there's an acid-base balance, it is an acid-base balance caused by something else. Maybe the patient has an overwhelming infection, maybe they're not perfusing very well, maybe they aren't breathing properly. Whatever the case may be, that's what's causing the acid-base problem. The acid-base imbalances do not occur in a vacuum. Okay, they don't occur. It's not an isolated thing. something else is going on to cause the acid-base balance, and if we see that, we need to put our little investigator hats on and figure out what the underlying cause of that acid-base balance is. Okay, so let's just talk about the body. The body has some built-in systems to deal with these imbalances. The body gets sick, acid-base, maybe there's too much acid, too much base, or something going on. The body has what are called buffer systems. And buffer systems prevent sudden changes in the pH. Typically, the buffer systems are typically associated with acid, with changes in my body's making more acid than it normally should. There are three primary buffer systems in the body that we want to look at. There's something called the phosphate buffer system. There's something called the protein buffer system, and there's something called the bicarbonate buffer system. We're not going to talk much about protein and phosphate buffer systems. They're there, they do a little bit of buffering. The majority of the buffering that occurs in the body is going to be the bicarbonate buffer system. Most of the buffering occurs. So when there's an acid-base imbalance, something's going on, the first line of defense that our body has is in a buffer system, and that's generally going to be the bicarbonate buffer system. It takes minutes to start compensating for that. The next line of defense is the respiratory system. That's where we come in. And what can the respiratory system do? Well, we can ventilate more effectively. Ventilation is one of those interesting words. It's often misunderstood, but ventilation is the technical definition of ventilation is getting gas into the lungs and getting gas out of the lungs. That's ventilation. That's not oxygenation. That's not getting oxygen into the blood and circulate around. Oxygenation is something a little different. Ventilation is the movement of gas in and out. More importantly, it's the ability to get carbon dioxide out. That's ventilation, getting carbon dioxide out. Well, carbon dioxide, interestingly enough, is one of the most important acids. And we'll talk about why it is an acid in the body, and you should probably have a pretty good idea from your past classes and the fact that we actually had to do a little bit of research on carbon dioxide and how it's transported in the body in your last assignment. But be that as it may, the second line of defense is the respiratory system. This generally takes hours to start compensating for this acid-base imbalance. And then the last line of defense, and what is generally considered the definitive line of defense, is the renal system, the kidneys. And the kidneys can work in a couple of ways. The kidneys can either excrete acid, get rid of acid if there's too much acid in the body, or the kidneys can hold on to bicarbonate. The kidneys can excrete acids, or they can get rid of excrete bicarbonate. I apologize, or hold on to acids. So the kidneys are nice in that they can regulate both the acid and the base, either by holding on or getting rid of acids, or holding on and getting rid of bases, or bicarbonate, which is the principal buffer in the body. Okay, so we know what an acid is. The Bronsted-Lowry definition of an acid. The Bronsted-Lowry definition of a base is anything that can accept, or in essence get rid, of a hydrogen ion, or hydronium ion, or a proton. The principal buffer in our body is bicarbonate. That's HCO3, a hydrogen, a carbon, 3 oxygens, and a bicarbonate molecule. It's negatively charged. It's a polyatomic ion. Because it's negatively charged, positively charged things like protons are attracted to it. And it can gobble them up, in essence, and buffer any pH change that would occur as a result of that. Okay, so we've got a nice little introduction to buffers, the different buffer systems. I want to quickly talk about the two major types of acid that we can have in our body. We can have what's called a volatile acid, and the only volatile acid in our body is carbon dioxide, and we'll talk about why that's an acid in a little bit. And then we have something called a fixed acid. And a fixed acid is something that the lungs cannot get rid of. The kidneys have to do it. And a good example of a fixed acid would be something like ammonia or hydrochloric acid. And basically what happens is with a fixed acid, it's generally a medication or some sort of metabolic cause. A lactic acid would be an example of fixed acid. The lungs can't get rid of these types of acids. Kidneys have to. When these acids disassociate, generally the reaction is irreversible. That is to say, if I put that acid in somebody, the hydrogen ion leaves, like hydrochloric acid, which is a hydrogen and a chlorine. It goes into the body, water, it splits up. That splitting cannot be reversed. I can't put them back together very easily. However, the reactions involving carbon dioxide, as we'll find out, are reversible. That is to say that carbon dioxide can be turned into bicarbonate, and bicarbonate can easily be turned back into carbon dioxide. And that's where we get 80% of our carbon dioxide being transported as bicarbonate. So carbon dioxide, volatile acid, we get rid of it through the lungs. Everything else is a fixed acid, get rid of those through the kidneys. Okay guys, take care.